All right, so we're looking at 6.2, which is dealing with relative extrema. So here are just a few notes before we get into looking at the actual problems. So basically we'll be given scenarios where we need to either find a maximum or minimum value on a particular interval or dealing with the constraints of the problem. So these are just some things that you want to keep in mind as you're going through the exercises in 6.2. First of all, of course, you always want to read your problems carefully when you're looking at a word problem. Make sure you understand what's going on and what are your unknowns or your variables in the problem. If it helps, it's good to sketch a picture of it, and of course you want to label it accordingly. Then you want to decide what are you trying to maximize or what are you trying to minimize. So if you read the problem carefully, it should tell you, are you trying to maximize something or are you trying to minimize something? Then you want to write your equation so that your equation only has one variable in it. Of course, you also want to keep in mind what the domain of the function is, because sometimes you'll get multiple answers, and depending on the constraints of the problems, some answers may not make sense. Then you want to find your critical points, because remember from 6.1, you're going to have a maximum or a minimum either at your endpoints of a closed interval or at the critical points on your given interval. So you want to find your critical points as well as looking at your endpoints to see what the max or the minimum is. And then, of course, 6 is just reminding you to just go back and apply the extreme value theorem if you have a closed interval versus an open interval, so on and so forth. So that's there for you to read, to just keep in mind. So now let's get into the actual problems. So your first problem says of all numbers whose sum is 60, find the two that have the maximum product. So you're trying to maximize Q equals x times y, where x plus y equals 60. So the domain for our problem is from 0 to 60 because, number one, if your numbers are negative, then that will reduce the value of your product. Or if both of the numbers are negative, then that would be the same as if both numbers are positive. But then, of course, if both of your numbers are negative, that will reduce your value when you add them together. So that's why it starts at 0. And then if their sum is 60, then the greatest that your number can be, if one number is 0, the other number has to be 60. Otherwise, if one number goes beyond 60, then you're going back to the negative numbers. So that's why your domain is from 0 to 60. And it's telling us to find the maximum product. We're trying to maximize Q, which is XY. So when you just write a little note here, you're looking for Q max. Then you take your information. You have x plus y equals 60. We want our equation in terms of one variable. So that way when we find the derivative, we're only differentiating using one variable as opposed to having an equation with two variables in it. So we solve one of the equations for the variable, and then we substitute that into the other equation. So if Q equals x times y, and if we can solve for y by itself equals 60 minus x, then we can plug in 60 minus x where y was in the original equation. So now we have x times 60 minus x instead of xy. So we simplified that. We find the derivative. We get our critical number as 30. So if x is 30, then y would also have to be 30 because we're going back to this equation where we already solved for y. If we plug in 30 for x, we get 30 for y also. And then our maximum product for q, which is x times y, is going to be 30 times 30. So that gives us 900. Moving on to number 2. It's a similar situation. It's just that our product is a little bit more complicated because we have a variable that is now squared. But because of the constraints of the problem, we similarly have a domain that starts at 0. This time it goes to 105 for the same reasons as number 1. And we're trying to maximize P. So P is in terms of x and y, but we want it in terms of one variable. So we can substitute out the y since it's already by itself in the equation. So we go over here, y will equal 105 minus x, and then we substitute that into p. We simplify p, we find the derivative, and then we look for our critical numbers when the derivative is equal to 0. So we get two solutions. We get 0 and 70, but we remember, or if we plug in 0 into the function, then that's just going to give us 0 for our product. So 0 won't work. And then when we plug in 70, that will give us our max. So we plug in 70 into the equation that we already solved for y. That gives us y equals 35. And we end up with a final product for P, our maximized product. When we plug in 70 and 35 for X and Y, we get 171,500. Number 3, a disease has hit a city. The percentage of the population infected after the disease is approximated by our function here between 0 and 40. And it's asking after how many days is the percentage of infected people a maximum, and what is that maximum percent. So you want to maximize P, so we're looking for P max. We find the derivative, we simplify it, we look for our critical numbers. We're going to get T equals 10. Now, because our function is a closed interval, we can apply the extreme value theorem. We check the endpoints at 0 and 40 as well as our critical number, and we see our critical number leads to our maximum value. So after 10 days, it's approximately 26%, and that is our maximum percentage. Number 4 is when it starts to help if you draw pictures to aid you in solving your problems. So it says a rectangular plot of farmland will be bounded on one side by a river and on the other 3 sides by a single-strand electric fence. You have 2,400 meters of wire at your disposal. What is the largest area you can enclose and what are its dimensions? So the picture helps us keep in mind that we're only enclosing 3 sides of the rectangle because the river is on the other side of the rectangle. So we're only, for our perimeter, we're only doing 2L plus W instead of 2L plus 2W because one of the sides is covered by the river. So we make our perimeter equation 2L plus W equals 2,400. And our area formula we already know is length times width. And we use the area formula because it's asking us what is the largest area you can enclose. So that means we want to maximize the area. So we solve the first equation where we were given a perimeter for W so that we can get our area equation in terms of only one variable. So W will equal 2,400 minus 2L. And then we substitute that into the area equation. So we substitute 2,400 minus 2L for W. And then we simplify, and then we look for our critical number. We get L equals 600, and then we plug that into the equation that we solved for W. We get W equals 1,200. So we want to maximize area. We plug those numbers in for length and width, and our maximum area is 720,000 meters squared. Now we're trying to build a fence to enclose a rectangular area, so there's no river this time, we just have a traditional rectangle. The fencing material costs $4 per foot for the 2 sides facing north and south, and $8 per foot for the other 2 sides. Find the cost of the least expensive fence. So we're trying to minimize the cost this time. We want the least expensive fence. So we have our area that's given to us this time. So we set our area equation equal to 20,000. And now we have a traditional rectangle. The perimeter is 2L plus 2W. But we also want to keep in mind that we're trying to minimize the cost. So we need to think about what our cost function looks like. Because It's $8 per foot on the north. I'm sorry, it's $4 per foot on the sides facing north and south. We put 4 next to the 2 L's, and we put 8 next to the 2 W's. And I realized I mislabeled it in the problem. I put the 4 here and the 8 there, but if you want to keep the orientation north and south, then it would have been 4 next to the part that had the W. But it doesn't matter in this problem that I did it that way, because both of them have a 2 next to it, and it will all work out because we're only looking for those 2 dimensions. So the length and the width of a rectangle is, in general, it's easy to swap out. So if I would have gone back, if I would be able to go back, I would change this to 8 and change that to 4, but it's not going to change the way that our solution works out because length and width are interchangeable. So if once you continue working it out, you have your cost function 8L plus 16W, or it could have been 16W plus 8L. Again, it doesn't really matter, but the point is that you're trying to minimize your cost. So you're looking for the minimum cost. So now we need to solve our area equation to get one of the variables by itself. So area is length times width equals 20,000. If you divide both sides by W, you have 20,000 over W equals L, or 20,000 W to the negative first power. That's the same as 20,000 over W. Then you plug that into your cost function, which you're trying to minimize. So you plug that in for L, and then you continue solving it. And you look for your critical numbers and your derivative. So this became negative 160,000. This was W to the negative second power plus 16. You subtract 16 on both sides. And then notice that I changed it from W to the negative second power. I just made it the exponent positive and put it in the denominator. So you multiply it on both sides to get here. Then you continue solving, divide by negative 16. And then take the square root, you end up with 100 for one of your dimensions. So we have W equals 100, so we go back to the area equation. 20,000 equals L times 100, so L is 200. So now we have our dimensions, 100 and 200, and our minimum area is going to be 3,200. Numbers 6 and 8 in your Math Excel assignments are identical to each other. They just give you different numbers for both problems. So it says a candy box is made from a piece of cardboard that measures 43 by 23 inches. You cut squares of equal side out of each corner. So basically these are your squares that you're cutting out. They're equal sides, so both of them could be X. And then the sides will be folded up to form a rectangular box. So once you cut these squares out, then you can fold your cardboard. You fold up the sides that are X distance long, and you end up with this shape. So notice that if you started out with 43 inches on this side, because you're cutting out a distance of X at the top and the bottom, that's why it's 43 minus 2X. And then the same thing with the distance going across. It was 23 inches, but because you're cutting out those X's, it ends up being 23 minus 2X inches. And then the height is still X because you're just folding this side up, and it's going to be a distance of X once it's folded up. So your dimensions for your volume is going to be length times width times height, and our length is X, the width is 43 minus 2X, the height is 23 minus 2X. Or you could move these variables all around. Again, it doesn't matter which you determine to be your length, your width, or your height. You still end up with the same equation. And then you want to maximize your volume. So we find the derivative of our equation. And here it is. And then you need to set it equal to 0 and solve it. I found that you can't factor it, so you need to use the quadratic formula. And then the two solutions that you get is 17.6 4.212 or 4.788. And notice over here that I determined that the domain had to be between 0 and 11.5. Obviously, you can't have a negative distance on your cardboard here, and your distance for x can't be longer than half of 23, because once it's longer than half of 23, then you don't have enough to cut out to fold this side evenly. So this could only be half because you have to fold the sides up to actually make a box once you fold them up. So that's why it goes from 0 to 11.5. And that excludes the 17.212. So that means that the side length for your square is going to have to be 4.79. Number 7 is similar. We have a box, but this time it's a rectangular tank, and the base is a square. So that means these two sides are going to be identical to give us a square bottom. So this distance is x and this distance is x, and the height is just going to be h for now. We're looking for the dimensions of the tank that has the minimum surface area. So we're using a different formula in addition to volume, which is still length times width times height. So x times h, which is x squared h, is 32 feet cubed, which we know because it's given in the problem. But our surface area formula, the surface area means you add up the area of all of the surfaces. So our base is a square, so that surface is just x by x. That's why we have x squared. And then the area of each one of these squares is going to be x times h. To get these, actually these are rectangles, but to get the area of these rectangles is going to be x times h. So that's why we have 4hx, because you have 1, 2, 3, 4 faces going all around this box. So you have the base plus the 4 sides going around. That's how we get our surface area formula. Now, you can solve your volume formula to get h by itself. You can divide both sides by x squared, and you'll get h equals 32x squared. So the surface area formula, if you make that substitution, is going to be x squared plus 4 times 32 over x squared times h. We just plug this information in for h into this formula, and then you simplify it. The x over x squared will just cancel. You just have one x in the denominator, and you multiply 4 and 32 to get 128. And then I wrote it because I'm going to get ready to do the derivative. So I rewrote it as x to the negative first power. And again, we want to minimize the surface area. So you're looking for the derivative of your surface area to find your critical numbers. After you simplify your derivative, you see that this will give you a undefined value at 0, and this will give you x equals 4. So our surface area is minimized, should be a D here, minimized when x equals 4. The volume we know was 32 feet cubed, and that equaled x squared times h. So we do 4 squared times h. We solve that, h equals 2. So the dimensions are 4 by 4 by 2. And be careful in Math Excel, they just ask you to type in all 3 answers at once. So just separate your answers by a comma. All right, so looking at number 10, before we move on to number 9, I found number 9 to be much more involved. So before we get to number 9, I wanted to do number 10 first. So number 10, you have a hunter at a point along a riverbank. He wants to get to his cabin, which is located 3 miles north and 8 miles west. He can travel at 6 miles per hour along the river, but only 2 miles per hour on rocky land. So he'll have to cut through the rocky land to get to his cabin. How far upriver should he go in order to reach the cabin in minimum time? So you want to minimize the time. He's walking along the river, which has a total distance of 8, and it's asking how far does he need to go upriver before he hikes through the rocks to get there in a minimum time. So again, we're minimizing time. because he's walking along this river for some distance, we know that the most that he can go is 8, and 8 is our limit. You know he's not going to go backwards into the negatives because he's trying to get there in minimum time. So that's why our domain is between 0 and 8. So we notice that this is the hypotenuse of a triangle where one side is 3. If this distance is 8, then that means the remaining distance must be 8 minus x. So the hypotenuse of our triangle, we use the Pythagorean theorem, h squared equals a squared, or 3 squared plus b squared, which is 8 minus x raised to the second power. And then we need to take the square root of that, so we simplify it here. This is our radical expression. Now, for our time equation, he's walking a x distance at a rate of 6 miles per hour. Time equals the distance divided by your speed, or the distance divided by your rate that you're walking. So that's why this is x divided by 6. And then when he's hiking through the rocks, it's his h distance divided by 2, because he's walking at a rate of 2 miles per hour. Again, time is distance divided by the rate. So we just rewrite that equation so that it looks a little bit neater. We have 1 over 6x plus 1 over 2h. Then from there we substitute. So we already determined h to be this, to write it in terms of x. So we have 1/6x plus 1/2 times this expression. Notice that I took it out of the radical and I wrote it with an exponent of 1/2. Then you take the derivative. Then after taking the derivative, we need to set it equal to 0 to find our critical numbers. So notice that in solving this equation to get to this step, what I did was I subtracted 2, which this is supposed to be a -2 here. And then I divided by the 3, and I divided by 2x minus 16. And I set that equal to the radical expression on the right-hand side. So the reason why this -2 didn't make a difference is because later I needed to square the whole problem anyway, so the -2 would have disappeared. Also notice that I'm raising it to the -2nd power because I want to get rid of this -1/2. These two negatives will cancel each other out, and then 1/2 times 2 is 1. So that will get rid of the exponent on this side. But now on the left side, because I'm raising it to a negative power, that means that I'm going to flip the fraction. So that's why the more complicated expression ended up at the top. And then when I squared the 2, the 4 was at the bottom. So I'm multiplying it by a negative, which flips it. And then because I'm squaring it, you have to put the 6x minus 48 in parentheses and square that. So when you FOIL it out, this is your expression. And then you can divide 4 into each one of these. So that reduces here. And then you have it equal to the right-hand side. And then you bring everything to one side to set it equal to 0. And again, you're going to have to use the quadratic formula here to get these two solutions. And then once you get both of these solutions, you have to remember your domain is from 0 to 8. So the 9.06 doesn't work. The 6.94 is going to be our solution that maximizes the time in our problem. Now, moving on to number 9. So number 9 says a cable runs along the wall from C to P at a cost of $10 per meter. So here is $10 per meter. Then it goes straight from P to M, and it costs $26 per meter. Let x be the distance from C to P, so that's our x. If M is 48 meters from the nearest point A on the wall, where P lies, and A is 106 meters from C, find x such that the cost of installing the cable is minimized and find this cost. So the problem is already illustrated for you. We just need to work it out from here. So notice that if this distance is 106, then this short distance here must be 106 minus x. And then again, you need to use the Pythagorean theorem to find h. So that's what we did here. And we got h to be equal to this expression. Notice that in this problem, we're using much larger values for our a, b, and c. So that's what ultimately makes the problem a little bit more complicated later on down the line. So the problem is telling us we're trying to minimize the cost. Again, our domain is going to be from 0 to 106 because that is the full distance that we have to travel up here. So we know it's going to be somewhere between 0 and 106. Our cost equation is 10 times x because as the problem said, it was $10 per meter for this distance, and then it was $26 per meter for this distance. So that's 26 times h. And again, we solve for h, so we go ahead and we substitute that value into the equation, and we're trying to minimize c. So my suggestion for you guys here, just to save your time in this one instance, and again, we've already done a problem like this for number 10, to save you time, you can go ahead and just graph the equation in Desmos and then use that to determine what your minimum value is. And I'm going to show you an example of what that looks like. So going over to Desmos, you would type in the function as we have found it thus far. This is our cost function. And notice that when you type it in at first, nothing actually pops up on the graph, so we can't see it. So now we need to figure out, well, where is this graph going to be? What do we need to do to adjust our window? So we know that our domain goes from 0 to 106. So we know it's going to be somewhere between 0 and 106. So we can make our x-axis go from 0, and I just use -1 so that we can still see where the y-axis is. And that goes over, and now my graph goes over to 110. However, even though it goes over to 110, I still can't see where the graph is. So now I know that I just need to change my y-axis setting. So let's just add on zeros here until we see the graph appearing somewhere in our image. So even if it goes up to 100, we still don't see anything. If it goes up to 1,000, we still don't see anything, but we know for sure that our graph should be somewhere between 0 and 106 on the right hand side. So we know it should be somewhere in this window. It's just a matter of how high or how low. The reason why I'm not going down in the negative direction is because we're talking about cost, and even though we're trying to minimize it, it's still not going to be negative for sure. So let's add on another 0. Now our graph goes all the way up to 10,000, but we kind of went way too high. So if you like your graph to look a little bit neater, you see that it starts at 4,000 here. So you can adjust this to 4,000, or you can just click on where your graph is. And here is what your minimum value is going to be. So your minimum x is, so your x that gives you the minimum is going to be 86 for your x. And this is our y value. So this is actually what our minimum cost is going to be. So x is going to be 86, and then the cost is going to be 2212. If you wanted to go back, instead of adjusting our windows to show you where the actual graph is, another option would have been to just also go ahead and graph your derivative and then figure out, based on what your derivative is, where your x coordinate is going to be. So now we can shrink it back down. Our black graph now is showing us what our derivative is. So just by looking at the derivative, we didn't even need to make our graph way bigger. That just gave us where the 86 is. So if you graph your derivative, that's going to show you where the function has its maximum or minimum, because you know your derivative is going to pass through the x-axis, because wherever your derivative is 0, that's where your x coordinate is going to be. That gives you that critical number for your max or your min. And again, just going back to the first and the second test, that means the function is decreasing. It has a critical number, and then it starts increasing. So that means that this must be our minimum value. Then all you would need to do is compute the function value when x is 86. And the calculator gives you that it's 2212. So now you know that you could just go and adjust your graph to go just a little bit above 2212 so you can see. So let's say 2300. Oops, sorry, this is our x-axis. Let's make the y-axis go up to 2300. And here is our minimum value. And of course, you could, play with the settings so that you can see more of the graph if that's what you're interested in, to see a better idea of what it looks like. You can change the numbers, but again, here's our minimum value at 86 and 2212. Now going back to doing the rest of the problem, if you are interested, here is all of the work that goes into it. Once you find your derivative function, you work it out, you solve it, much like we did for the previous problem. You continue solving it. You need to raise it to the negative second power. You flip the left-hand side, and then you solve. You continue solving for x. This is just a whole bunch of simplifying here and solving. Bring everything to one side, set it equal to 0. You still would be using the quadratic formula to help you, unless you just really want to go ahead and try to factor it. Eventually, you will get the factors if you just keep trying numbers, but it's a lot easier to just go ahead and plug it straight into the quadratic formula in this case. You end up with the two solutions, 86 and 126. The 126 is outside of our domain, so 86 again is the number that works, and you plug that into your cost function from earlier, and that will end up giving you 2212. And we've already seen that it's correct on the graph, so that's just two separate ways of looking at it. Again, you can just zoom through this one a little bit faster because you would already be doing similar steps in your other problem in this assignment. So this is all of your problems for 6.2. I look forward to seeing you guys soon. Good luck.